Good afternoon, everyone. We are in Palace 1, and the name of this talk is Press Route to Continue, Detecting OSX and Windows Botnets with RDFU. I'm going to hand you over to your presenters. Thank you.
Hello, my name is Vuksan, and we're here to talk about actually Bootkits for UEFI. Really, again, I'll thank people for moving forward. Unfortunately, the UEFI is not, tabloid sized, and also it's not in Technicolor, so letters will be smaller, and there'll be definitely lack of color. But we nevertheless, find it very exciting and interesting. And I would like to begin by telling you more in terms of how we're going to structure this talk. We are obviously interested in telling you more about our motivation. UEFI is not everybody's cup of tea. It's not really written about all that much, although in the last few years, we are seeing more and more research. We also would like to talk to you more about who we are, as we have been regularly speaking in Black Hat, releasing various open source projects. And we find, this research being relevant extension of what we've been doing. Also, we'd like to then follow up with a sort of brief introduction to UEFI. I'm sure a lot of you are very familiar with it, but nevertheless, it's sort of good sort of to set the stage, and then also to mention some of the previous UEFI Bootkit research. Some of it presented at Black Hat, very good material that was certainly influential in our own work. And then we want to get into the actually presenting the rootkit detection framework, or what we called RDFU, by looking at the framework design, discussing reasons that were behind its structure, and then also going through the VMware implementation demo. And then obviously every good defense measure comes with a proof of concept material to validate it. So we will at the end of the talk demonstrate the macOS 10 bootkit. Now, to start with, it's really our motivation, and so we as a company have always been very much interested in the file-borne threats, deep file analysis. And after having spent a lot of time with Windows, with ELF, documents, firmware, mobile packages, we really said, hey, it'd be really, really interesting to do a deeper dive on the firmware level. So we obviously noticed that UEFI's popularity these days is really paramount, as it runs on Windows platform, runs under Android, runs under macOS, and it's actually everywhere. And not just only that it's everywhere, it's extremely powerful. UEFI today is full stack OS. It has all the cool things you would want out of an OS to allow you to write really, really cool applications sitting on top of it. And obviously, it's extremely, extremely interesting for exploitation at that point. So it has a special set of powerful memory and file manipulation features. It has a full network stack, which is definitely very, very important for the exploitation. But then also it has lots of really other cool things, such as graphic APIs. So you can imagine the vulnerability research in that area could be extremely, extremely useful. Has a great device management capability, and then also has ability to do a remote boot. So you pretty much have all the elements to be able to do really, really interesting and wonderful attacking components. Now, beyond these set of features, UEFI is really attacker's paradise, because the defenders definitely have a lot of disadvantages in the area. It has definitely low visibility, because there's very few tools that actually do anything about it, detect any presence or malformation or invalid traffic originating specifically from the UEFI stack. Then also, if you were actually trying to investigate malicious firmware image, here a malicious UEFI image, it'd be very difficult for you to set up a nice off-the-shelf tool stack. Largely, you would have to build your own things. It would be extremely painful. A lot of stuff would be hardware connected. Odds would get stacked against you in actually trying to easily and quickly analyze what's happening. Of course, there are in this story lots of also good positive elements. I mean, UEFI has been around, has been developed here, almost in vacuum from actually in-depth security analysis. But what we have seen with the UEFI Secure Boot, especially on some Android devices and Surface RT, is definitely very promising. It's a much higher security strength that we have ever seen on UEFI, and we are really hoping that most of the new devices will be shipping with Secure Boot enabled. Now, a few words about who we are. So the company was founded, by two of us, me, Mario Vuksan, and Tomislav Pericin over here. We started the company in 2009, and our focus has always been the deep binary analysis of a wide range of executable formats. And while doing the analysis, we really tried to pull out as much material out of those formats, specifically trying to understand the reputation of various components, malformations, and different anomaly detections. Now, in our process of developing some commercial products, we have been very, very interested in developing a wider range of open source and freeware tools. We started in 2009 with something that's called a Titan Engine, which is a really a library for portable executable format reconstruction, and has been successfully used by various organizations in building, from custom unpackers to vulnerability scanners, and even some pen testing projects. Then we really took a deeper dive into archive formats. We released in 2010 something called Nix Engine, which was the archive format stego detection tool. Something that only recently, with Blue Box Android announcements, has actually come a full circle. We have realized that we have had a tool to detect these really more like stego hiding artifacts inside of Android APKs, and we believe that this is sort of really interesting area to go back to and try to see how the archive formats actually can be misused in an executable environment. Following our Nix Engine, we tried to put together an open source platform for actually unpacker writing, analysis of Windows binaries, which we then followed with an unofficial guide to P malformation. Probably some of you came to that talk a couple of years ago. We were really surprised how many people were excited about always new things that you can learn from PE. So for us, that format never ceased to surprise us. And then last year, we started a project that was our first cooperation with the DARPA CFT program, and we have released something called the File Disinfection Framework, which is an open source platform that allows people to actually write disinfectors, disinfectors for various file infection attacks under Windows. And this obviously brings us to this year's work that on UEFI that has also been funded by DARPA CFT. So having said that, obviously we would love to thank DARPA CFT for being such a great program that has allowed us to work on things that were, things that we are really interested in, that we wanted to do, but were slightly outside of our, commercial offering, but nevertheless relevant topics for the community in general. Also, we would like to, explicitly thank to, several researchers that have influenced this presentation and whose work we'll be citing as we set the stage for talking deeper about the RDFU. So we want to thank to John Heisman, who spoke at Black Hat in 2007. We want to thank to Snare from Assurance, who spoke last year. Really great talk here at Black Hat. We also like to thank to Dan Griffin, who spoke only a couple days later at DEF CON, and Sebastian Kaczmarek, who had an interesting Bootkit talk at the Hack in the Box in Amsterdam just a few months ago. So without further ado, I want to introduce you Tomislav, and he'll continue with the UEFI.
Hello, my name is Tomislav Pericin. I'm the Chief Software Architect at Reversing Labs. I'm the guy behind, one of the guys behind all of the projects Mario has mentioned so far. Today we are focusing on the UEFI and our latest project, which is sponsored by DARPA. So how does the booting process look today on machines that do not have UEFI? So this is the old version of loading the operating system. So you start with the BIOS, which is the basic input-output system. You load the operating system through iterating through the MBR. That is all executed in real mode. The control is then passed to the Windows components, which then initialize the kernel, run the other hardware abstraction layers, create sessions, and so on. This is the old module which still is in use today on the older machines, but if you have bought a laptop or a PC recently, within the last couple of years, you most commonly have a thing called Unified Extensible Firmware Interface. So what it is, it's a set of tools that enable people who create devices to really easily create new protocols and support new devices. It was originally developed by Intel with something which is called Intel Boot Initiative. It is being worked on ever since, and it's now grown into a community effort to modernize the PC booting process. It currently ships as a boot option alongside the standard legacy BIOS, so you have to turn it on most devices. When you choose to install an operating system, you have to have that turned on to be able to actually install UEFI. Other operating systems like Windows also support secure boot, so that enables you to have much more security when you're installing an operating system to make sure that all of the components have not been tampered with while you are booting into your operating system. So the UEFI aims to be the future, the only booting interface in the future. It is used today in all Intel-powered MacBooks and PC as well. It is managed by the Unified Extensible Firmware Interface Consortium, and you can find and download the specs from their website. It's a pretty good read, even though it's like 2,000 pages. There's quite a bit of elements there which you can find, which are really interesting. Most of those were used for this particular talk, that enabled us to create RDFU. So how does the booting system change when there's unified extensible firmware interface? So the only thing which actually changes is there's no more BIOS. All the firmware gets initialized by the UEFI. Then the UEFI goes through the list of available devices, loads the boot manager. In this case, we've highlighted the Microsoft boot manager, which then selects which operating system it wants to load. Then all of the remaining things happen as they were before in Windows. So the UEFI is something which boots up the machine, but it also leaves the remnants running as long as the PC is powered on. So in a nutshell, this is a conceptual overview of how this entire stack looks like. So on the top you would have the operating system, and on the bottom you would have the EFI operating system loader, which initializes the entire process. So the EFI consists of the boot services, which are really important, runtime services as well. So those are going to be the things we talk about next. In addition to that, you have the underlying layers of the platform hardware, which is abstracted by the Unified Extensible Interface firmware, which enables you to communicate with the devices, to create new protocols, and so on. All of that is contained on an EFI partition, and that is actually installed by the operating system. So when you create a new install of Windows, for example, you would basically get two new partitions, one for the EFI layer and additional Windows partition, which actually is used for storing additional Windows data. Following that, you have other parts of the disk which are used by the user. So the boot sequence has changed a bit. So here is how it looks like today. All of the green items are the things that happen with the boot manager's assistance. So you initialize the platform by loading the firmware, and then the firmware takes off by loading other interesting things which need to be loaded, like EFI drivers. All of those drivers have an option of running additional applications, and all of that is to assure that all of the devices you have on the machine are actually communicating properly. Once the booting process has completed, the EFI searches for the OS loader code, and it boots up that specific application, which then calls a function which terminates the booting services, which actually shuts down part of the EFI drivers, which are just meant to be running as the device is booting. Once that happens, the control is passed to the operating system, which then continues on normally. So with that in mind, there are a couple of different things we should really know about UEFI images, and that is that they are typically portable executables, which is the most important thing for us, because portable executable format is something we have been talking about in the past, and this is just one subset of that format. That's why this was of interest to us. But in addition to that, the standard actually predicts there are other formats as well. So basically any vendor can create any kind of executable format they want. So Intel designed this format called T, and it is being used by Apple as well in their implementation of the UEFI. So even though UEFI is a standard, and anybody can basically use any part of it and create a standard of their own. Basically that includes the UEFI images as well. That was the case with the first version of the UEFI specification, which was 1.10. The later specification, so 2.0, which is the more current, is much more strict in that regard. So you have two types of UEFI images. You have drivers, which yet again there are two types of drivers. You have the boot service drivers, which are actually terminated as soon as the operating system loader calls the exit boot services. So at that point all of the drivers which are just boot service drivers are unloaded from the system, and the system is continues with the loading. You also have the runtime service drivers, which are present all the time. So as long as the application or the system is running, all of those drivers are also running as well. So that becomes a really nice way for you to inject any kind of code which actually runs as long as the machine is running. And that is what our project is focused on, finding these images and letting you know that they are present in the system. So those were the drivers. There are also applications. There are two types of applications, like the normal applications that actually exist and execute only in the pre-boot environment. I'm going to show you how that looks like later on during the demo. And there's a specific UEFI application which just loads the operating system. And that's the only kind of application which can actually take control of the system by calling the exit boot services, which then later on unloads all the drivers which are the boot service drivers. So how do these programs communicate with the firmware? There's this thing called boot services and runtime services as well. So boot services are, you can think of it like a set of APIs which are available to the developers, which are actually creating programs that run in the UEFI environment. And they consist of functions which are only available before the exit boot services is called. So these would be the boot service drivers. So they have functions which can be categorized as global, so they are available everywhere, and they're also handle based, which means that you can dynamically create protocols by applying many of these handle characteristics to handles that are already open. By opening other handles, you basically create protocols. So you have global functions which are available on all platforms, that is by UEFI specification. So you have event, you can do basic tasks with these kinds of APIs, like create events, timers, allocate some memory, handle other protocols which can be available if a specific device and driver is installed. You have image services which enable you to communicate with other loaded drivers, and you have other miscellaneous services as well. So handle based are specific functionality. They're not available everywhere, and they're only there if you create a handle or there's other devices other device drivers which have created that handle as well. So those were the boot services. You also have the runtime services, which are available throughout the actual loading process. So as long as the machine is running, those runtime services are available. Yet again, these functions are also global and handle-based, and you can dynamically create them as well. Unlike the boot services, these ones can offer different kinds of things, like runtime rules. You can create those as well. You can access the variable services, so you can also create, you can access time and other things like keyboard and so on and so forth. They're also handle-based as well, so you can create more on the fly. So how do developers actually use these kinds of available tools? So there's a specific package available online. It's a free download, and it's called an FE development kit, or EDK2. It's based on the Intel's reference implementation, and it enables you to write EFI applications in C. It does have its own standard lib implementation, but it's not really the C you know already. It only offers a small portion of the C library, and that is because it's been basically wrapped around these available services, which basically enable you to allocate memory, communicate with devices, and so on. So only a small subset of C programming language is available. However, it's good enough for you to actually work with memory, allocate pointers, and so on. That enables you to easily write EFI drivers, and I'll show you an example in a sec. So it has a lot of packages which are available there as well. It has a shell, so you can actually type stuff in command line. It has crypto functions. It offers some emulation capabilities. There's even a Python reference implementation, so you can even use Python from the EFI layer to script around your drivers and do whatever you want with that. When you write those applications, the EDK actually supports to use many different compilers at all. You can use Visual Studio's compiler, you can use the GCC one, you can use the Xcode. It's all fine. It all compiles almost to the binary exact images regardless of the platform you used. So it supports many different CPUs, so EA64, which includes both 32-bit and 64-bit architectures, and ARM architecture as well. Here you would have a sample of how this application would actually look like if you were to write it with the help of the EDK. So it's a standard C application which has the number of arguments passed to the program and all of those parameters as strings as well. So this is something you can use from the EDKs, but this is not the way you actually write UFI applications. This entry point which you created here, so shell app main, is basically wrapped around the natural way the UFI applications are written. So the next slide actually shows that. So this main function still takes two parameters. So the first one will be the handle of the image you are at, so handle of your image, and then you have a pointer to the system table which actually consists of pointers to boot and runtime services. So these are the functions you can actually use, and the previous example was just a wrapper around this to make it more like C code, so C programmers feel at home. But we would be using these pointers natively because they enable us to access functions which enable us to create events, to basically inspect memory, to see other images, to access firmware, and so on. The functions are located in this kind of structure. So naturally, there is a way to actually abuse all of this unified interface as well, because all of that is pretty much open to whoever's writing the driver. So if you write a driver, you have access to the entire machine. There's almost no restrictions about you accessing a part of the memory. So you can imagine like writing a user mode application but having all of other drivers loaded in the same address space. It's basically like that because you can access all of the memory regardless of memory permissions at all. So you can install hooks, you can override drivers, you can unload images. Basically the EFI layer is trusting you to do the right thing, and you might choose to abuse that as well. That is why the concepts like secure boot have been introduced as well. So there has been some previous work and research about bootkits and how you can create those as well. The previous work which happened in 2007 was presented here at Black Hat, and what they did is they modified the NVRAM variables, they injected some code, and they showed how you can abuse system management mode basically. That was followed by last year's talk which Snare did, and he showed how you can patch the macOS kernel if you had a maliciously loaded EFI driver. And he introduced the concept of evil-made attacks for the EFI layer. And just this year at Hack in the Box in Amsterdam, one of the first bootkits for the Windows 8 was presented. His approach was quite similar to ours. If you compare the way that Dream Boot works and compare the way our macOS bootkit works, they're quite similar in the case that you have to hook certain things and you have to inject code as well to be able to execute commands at a much higher level. We'll go in a bit more detail later on of how did we create our own bootkit. But here is a simple diagram which shows how Dream Boot actually operates. At certain layers, hooks are installed which redirect code to maliciously loaded drivers, which then install callbacks which are executed when certain events in Windows happen. So that enables privilege escalation attacks and so on. So that brought us to RDFU, which is a rootkit detection framework for the UEFI layer. It's, as we mentioned before, it's a DARPA-sponsored project, and we'd like to thank DARPA yet again. So what actually is RDFU? So RDFU is a set of applications and drivers that enable you to list all loaded drivers in the EFI environment. You can probe the entire memory range, you can scan for executables that might be hidden, you can monitor all drivers which are loaded before the operating system starts, you can start listing and scanning the boot and runtime services for modified function pointers that will be shown as well. So if checksums are not matching on specific images, that is displayed in the log. All of those files are automatically dumped as well, so you can analyze them later on as well. We are also continuously monitoring both the boot and the runtime services while the operating system is being loaded, making sure that none of those modifications occur while our RDFU is loaded. We can also list all events which are happening, and it also works as a standalone because the EFI specification says that shell is absolutely optional, so you might choose not to implement shell if you don't want to. RDFU would work even though if there's no shell, so it comes with its own graphical user interface which you can use to access all of its functionality. So what does it support? It supports both the older specifications, so 1.x, and the latest one for both 32-bit and 64-bit environments as well. It supports a specific macOS implementation of the UEFI. It works under VirtualBox, even though VirtualBox currently, the latest version I checked though, does have an EFI shell, but it's incapable of actually installing an operating system under EFI. They are still working on that. VMware has much better support and you can actually use the EFI layer. It has a shell, you can actually install the operating system and it works just fine. Currently we do not support EFI for ARM because there's only one implementation, and that's Surface RT, and that implementation already has secure boot enabled by default, and that's why we opted not to support that one, because you should be pretty safe and there's no need for you to actually scan those devices. So how does RDFU work? There's a couple of options. You can actually load the driver if there's an UEFI shell enabled. You can create a bootable thumb drive which you can just plug into the machine, and then the RDFU would be executed automatically. Then you can actually scan your entire machine for drivers which should not be there, or modified firmware as well. Then it has a scanner application which works under UEFI shell. You have to actually have UEFI shell to execute it. While it's executing, it's logging and dumping all the information which it finds onto the mounted hard drive or to the thumb drive from which it was loaded. So here is an example of how that would look like. So this is you actually using the RDFU framework under VMware. While you are booting the system, you would actually just press a button to select the boot manager. That brings you to the option of actually selecting which kind of boot device would you like to load. There's an option called internal shell. Even though it says it's an unsupported option, it actually works just fine. So you are prompted to the shell of the EFI interface, where you can actually start and load the RDFU, which comes with its loading screen and then comes with a set of options which enable you to do all sorts of cool things. So it has a lot of options. The first would be to list all the handles which are present in the machine. That would be equivalent to protocols as well. You can list all images, dump all images to the disks. You can later on inspect them. You can check the pointers. You can list all the events. You can basically brute force scan the memory to try to find any images which should not be there. So if somebody has dynamically allocated memory and put an image there to basically execute it, that will be detected as well. You can display the memory map. You can dump the firmware, show the IDT and GDT as well, and you can install resident scanners. That's an option which enables you to actually install RDFU so it monitors the entire loading process until the operating system starts. Now this was us actually running EFI from shell. Other things have been loaded before this, but the EFI shell comes with a startup script which enables you to install this as a resident scanner, so it's automatically executed every time you boot the machine. There's that option, or you can actually manually install it if you have root privileges or you are actually simulating the process of installing an operating system. So we're going to show a demo of how this RDFU actually works. I'm going to be using the VMware implementation, so to show that that works correctly. So we've started the. Oh, sorry. I actually have to do this. So as I mentioned before, you'd have to select the boot manager option, and there you have the internal shell. When you go back to that, it actually loads and it enables you to do shell commands. So things like listing files and so on can be supported depending on what the actual implementation of Unified Extensible Interface you are working with. So this one actually has our RDFU installed on a separate hard drive. So here I've mounted that drive and I've shown you that all of those things are there. So all I need to do now is load our scanner. So load EFI scanner application. This is a 64-bit application, so we are loading a driver which will show the logo of our tool, and then following that you'll have all of the options which are available. So for example, we're just going to list all of the handles which are available, and we can dump the firmware as well. So we can dump the firmware ROM, that's G, and that's now dumped on the same hard drive. You can actually do your analysis there. You can do brute force scanning for other installed EFI drivers. That will be listed here as well in the log. So we're just going to quit now, and I'm going to show you that DFI actually comes with with some tools which enable you to actually inspect this without actually going to Windows or any other operating system to actually view those things. So this will be just you inspecting that log with a text editor which is basically available with this implementation of the EFI shell. So at the end, as you can see, we've dumped the firmware. It's on our USB thumb drive, and you can inspect it later on, load it in IDA Pro or anything like that. So that is how the RDFU works. So next we will be So one sec. So next we will be talking about the specific bootkit which we ourselves wrote for the Mac OS. And we will go into details of how this bootkit was created and what was our intention with this tool as well. So we had a goal, and that was to do certain things which normal bootkits and rootkits would be doing, and that is creating hidden content, so creating hidden folders, even restoring that. Restoring those folders as well. So we wanted to be able to hide running processes and show them back again as well. We wanted to have an ability to elevate privilege and have a shell which gives us root privilege so we can do anything we want. And the bonus points would be us retrieving the default file vault password if it was available. So how does this bootkit work? So we've tested this on the live Mac OS machine. We don't have one present today. However, the VMware implementation will suffice. So for that, if you were using this on a live machine, the option would be just using the RDFU to create a bootable USB thumb drive, which can enable you to basically boot an OS. To that thumb drive, you just copy our bootkit code, which automatically scans all the partitions and then selects Mac OS, loads it, and does all of the things we mentioned in a sec automatically. So since we don't have a MacBook present, here is what we opted to do. We wanted to do this in VMware. So the VMware is perfectly fine because Mac OS can run in it. It runs in it only if you have an unofficial patch, sadly. So you have to patch your VMware to be able to actually execute Mac OS under it. And the only thing you have to add after that is make sure that the VMX file has the firmware option EFI enabled. That enables the VMware to actually run with the EFI interface. After that, Mac OS is installed and it has a support for the version 1.10 of the EFI standard. So how does the bootkit work? Here's a typical workflow. The UEFI is loaded. It loads our malicious driver, which then registers for an event, and this event is called virtual address change, and that means that when this event is fired, basically the operating system is being loaded. So all the drivers which are still running, all the runtime drivers which are still running have to adjust for transitioning from the physical addressing mode to the virtual addressing mode, and this is what this event will do. We also hooked a specific system table function, which is read keystroke, that enables us to actually sniff all the keys the user has typed in while booting the machine. The idea here is that if file vault is installed, then the user has to enter the password, and that comes through the keyboard. So since we are logging all the keys, we would get this password once the system is loaded. So there's a failsafe unless if something goes wrong. We've registered ourselves for the unload protocol, which means that our loading has failed and we just have to basically clean up. After that, we have to load Mac OS because our bootkit has been installed. So loading Mac OS is basically enumerating all drives which have a specific EFI image present. User has a choice of selecting which EFI, boot EFI gets loaded if there are multiple ones, but if there's just one found, we automatically boot to it as well. So we just call load image to load that EFI image, and then we start it. So at that point, Mac OS starts the booting process, and we get signaled by the event when the Mac OS bootloader calls set virtual address map. So that triggers that event which I mentioned, which is the virtual address change. That tells us the Mac OS is ready to be booted, and that the next command it will call is the one which actually unloads all the drivers which are running only during the boot. That triggers the part of the code which actually locates the syscall table, and from that syscall table we are just hooking a few functions which enable us to do all those things we set to do. So we are hooking the setUID, get directory entries, get their attributes, and syscall as well. So how do we actually get root? This is a small C application which actually enables you to get root. So we tried to set our user ID to a specific number. This specific number has been hard-coded inside the bootkit. So as soon as our bootkit in the kernel level sees this user ID, it knows to elevate the privilege of that process to root. So how do we hide processes? This is yet another short snippet, which is basically us running a syscall event with a set of parameters which are analyzed by the bootkit itself, which then knows what to do. And in this case, it is just adding a new process to be hidden. So with that, we have a demo of how that actually works. And let me just boot up macOS once again. So yet again, since I'm using the VMware implementation, this actually has to be done manually. If I was using a physical machine, I could just plug in a thumb drive and all of this would be happening automatically. The only thing I had to do is select that I want to boot from a thumb drive. So this, I go to the internal shell option, and then I basically just go to the mounted hard drive and load the bootkit code. That automatically finds the macOS partition, it loads its bootEFI code, and it's patched all the things behind it. So what's happening now is the OS is loading. That could take a while since we are on the virtual machine implementation. Once we have booted, I'll log in and I'll show you that all of the functionality which we mentioned, which is hiding processes, hiding folders and so on, actually does work. So we're loading, and that's going to give us into the shell. So here, as you can see, we can do all sorts of things. Here I have all those applications written in C. They have all been compiled, so we don't have to do that again. So let's do the first thing first. Let's hide this process. So the process ID for bash currently is 140. So I can just add PID 140, and that's going to be hidden now. As you can see, process list is basically empty. We can unhide that as well by remove PID, so the same PID, and then we can show that this process is now visible yet again. In addition to that, we can create a hidden folder, so MK there. So it's actually hard-coded to this first string, but the other part of the string you can type in anything you like. So a listing of directories actually doesn't show this one, but it's accessible anyway. So we are in this folder. There are no files there, but we can just create one. And as you can see, there's a file there now. So we can just remove that since we don't need it. And go back one level to remove that folder. So yet again, the folder is gone, but it wasn't shown there as well. The last thing we need to do is to elevate privilege. So currently I'm a user, but if I wanted to get root, all I had to do is execute shell. That C code, as you remember, has only 2 lines. So executing shell, and then we got root. From this point we can do anything we like. We can even install our bootkit permanently by accessing the EFI partition and installing it so it loads every time. So the bootkit right now it is loaded, but if I were to reboot it would not be loaded at all. So all of the changes I've done would not matter. So all of those hidden folders would be visible. So the bootkit is only in memory. So that concludes the bootkit presentation. And that brings us to the reminder of our talk. So we've done all this, and here that was the demo. So what can you do with RDFU? You can use the EFI shell, some of its functionality, even though even if there is no EFI shell available. As I said, the documentation and specification does not require shell to be present. You can check which are the installed and loaded EFI components. You can scan the environment for hidden ones, and you can actually modify its source code to make it act like secure boot. So you can actually check all of the installed and running drivers, and you can unload things you don't like, or you can just report them as well. For that, you would have to modify the source code. Which brings us to where you can get it. So it's available on our website now. You can go and download the source code. You can get almost everything. The only thing we have not published is the Bootkits source code because this was a DARPA sponsored project. We wouldn't be feeling comfortable to release a code which actually does malicious things. So the scanner and its source code are actually available on our website right now. That concludes our talk, but we will be taking questions and answers. So, go ahead.
So when the Bootkits or whatever is loaded,
yep.
And you said you can permanently install it.
Yep.
Are you guys have some other hooks in there to prevent it from being uninstalled, or is there a specific sequence that you have to do to kind of unload it?
So the Bootkit, so how can you install a Bootkit permanently? And you do that manually by basically writing it over the original loader code. So for the Mac OS, and then you can just rename that to any other application and load it normally. So you can do that. How would they remove it? The EFI partition from the EFI layer is read-only. So the only way to actually remove it is from the operating system. So the same way we install that, you can uninstall it as well, just by overwriting it with the original binary. With the RDFU, no. RDFU is just a scanner. It doesn't prevent anything. It just reports things. Yeah, you have a potential to do that if you modify the source code. Then you have you can basically go through the entire file system, make sure that those images are still correct, and you are basically implementing your own secure boot. Any other questions?
So these boot services or Vuksan services functionality actually on active, or is it loaded from the hardware?
It's actually loaded by it's available through the firmware. So the firmware is the thing which enables you to use this functionality. It's actually in the ROM, and you can actually dump it with our tool.
Can you load RDFU from the OS?
No, you have to be at the EFI level, but you can create a bootable thumb drive, which just enables you to boot RDFU normally, and then just run the operating system after that.
No OS level usage?
No, there's no OS level usage of it. It has to be loaded before the operating system. Anybody else? So if I'm not missing anybody, that will be it. Well, thank you very much for your time. Thank you.